So if we are to calculate the shearing force and the bending moment of an uniformly increasing load, the method we are going to be using is something similar. So we need to understand the concept of UDL and other ones in order for us to be able to understand this well. So now the shearing force at point A here, the shearing force at A is equals to, obviously is equals to 0, because we have our unit run times our unit run times distance, which is 0. But now before we move on, we need to understand something, that the load here is given by Wx over L. That is the load, what the load is given by. That is the total load is given by Wx over L, where x is the small distance while L is the total distance. So at the end point here, the total load will be given as W. That is how it looks like. So, and the load can also be interpreted as the height. The load can be interpreted as the height. So if we are calculating the shearing force of this, we need to be able to understand the concept of area. So we are going to look at shearing force here as the area. So now calculating the shearing force of any point here is the area of the triangle at that point. So let's say at x here, if I bring this triangle out, so we have this here, which is here. The bottom here is what? X at point A, this point x here. While the height here will be Wx over L. That will be the height here, because that is the load at any point in this place. So now the shearing force here, the shearing force at point X would be equals to half base. The base is x times height. The height is Wx over L. Wx over the full length. So now the formula will now be equals to 1 over 2 times Wx square over L. That is Wx square over 2L. Negative, don't forget the negative part, because the load is downward. So now the formula for this is the shearing force at x is equals to minus Wx square over 2L. Now that is the shearing force at that point. So now the shearing force at the end point is very easy. So the shearing force at point B here would be equals to minus, now we can use our normal formula, half, what is our total base? Our base is the full length, that is from A to B, which is length, base times, what is our height? W times x over L. But the x now is the distance, and the distance is the full length, that is W times L over L. So L will cancel L, which will go out, and we will have it as minus WL over 2 as our shearing force as B. Now this is the formula for shearing force right here. Now for our bending moments, our bending moment at A is equals to 0 kilonewton meter as usual. All these ones are kilonewton, kilonewton, kilonewton. So here 0 kilonewton per meter. Why now the bending moment at x, what is it going to give us? So at earlier I mentioned that the bending moment of any load, bending moment of any this thing is the shearing force times the distance at the times the distance at the centroid. But now where is the centroid of a triangle? If I have a triangle, I cannot say that the centroid is at the middle of the triangle here, because if I balance this, if I try to balance this on a pivot, it's going to bend to this other side. So I have to balance it at 1/3, of the triangle, where the distance between here and here is 1/3, and the distance between here and here is 2/3. That is where the centroid of a triangle is located. So now we are asked to find for the bending moment of x. So now we have our shearing force at that x to be half times base, which is x, times the height, which is wx over l, which we later got as wx squared over 2l, as in minus. Then we have to multiply it by the distance from the centroid. The distance from the centroid, it will be times 1 over 3 and 1 over 3 times x. That means I'm dividing that triangle, the triangle which we get here, which the bottom is x, you divide it by 3 and you pick this 1 over 3 side here. That is where the centroid. And if you do not understand that, you can look at it this way. After getting the shearing force, this section that we add here, that was a triangle form, you can imagine that it has now become point load. It has become point load at 1 over 3 of x. That is when you divide x by 3, that is the distance between here. When you divide that point by 3, you have gotten the distance like that. So here will now be 2 over 3 of x. But we are finding for the distance between here and here, that is 1 over 3 of x of that triangular. So that's how we got this. And then our final answer of this will be minus wx cube over 6l. So that is how we got our formula for the bending moment as minus wx cube over 6l. So then the bending moment at the final length, the bending moment at B, which is the total length, that should be equals to, we have the shearing force here at minus WL over 2. We have minus WL over 2 times the distance from the centroid. The centroid will be at 1 over 3 of that L. That is times 1 over 3 times L. So this one answer will be minus WL squared over 6. So now this is the answer for the bending moment at B. So if we are asked to draw the shearing force diagram and the bending moment diagram, is going to be something like this. We have our neutral line for the shearing force. At A, that is 0. Then at B, we have minus WS squared times 2L, and at that is at X, and at B, we have this. It will be a cubic curve. It's a cubic curve. But you cannot really actually differentiate between a parabolic curve and a cubic curve. So you just have to make sure that it's some kind of curve, and you can differentiate it with you can differentiate it with 3 degree, which means that it's a third degree line. It is a third order angle. Then we have our negative here. Here is minus wx over 2l. No, sorry. Our shearing force here is a 2 degree line. Our shearing force here is a 2 degree line, but our bending moment is going to be a 3 degree line. Then at here we have minus WL over 2 for our shearing force. And then for our bending moments, we have this. This is going to be a 3 degree, a 3 order line. Then here our bending moment at x is minus wx over 6l. We have 6l. Then here our bending moment is minus wl squared over 6, minus wx cube over 6l, and minus wl squared over 6. So this is the shearing force diagram and the bending moment diagram of a triangular load.